section 5.3 is all about independence and the multiplication rule. So the addition rule has the word or, and that's when you're performing one event, okay? You use the addition rule. So when you use the addition rule, if you're performing one event and you see that word this or that, you're going to use the addition rule. When we have and we're performing multiple events, can't write today, multiple events, we're going to multiply. And I'll point that out again when we get to the rule, okay? So on objective 1, it says identify independent events. Just like we had that definition of disjoint or mutually exclusive where they were separate, we could do the easy A plus B. It's kind of the same thing here. If two events are independent, it means the occurrence of event E in a probability experiment does not affect the probability of event F. Mainly, if I do E and it doesn't change my probability of F, then they're called independent. They are not affected by one or another. Two events are called dependent if the occurrence of event E. So if E happened first and it affects the probability of F, they're dependent. And we'll do some right here in a second to kind of make that make sense. So if you're okay with that, flip it over to the top of page 7 because I think jumping into the examples makes more sense than anything. Say my first experiment is rolling a die, and then I get a 4. And then my next experiment is pulling a 10 from a deck of cards. Was getting a 4, did that play any kind of change on getting a 10 from a deck of cards? Did those two things have anything to do with each other? No, I could have rolled a 1, 2, 3, 4, 5, 6. It did not matter what I rolled on that die. It did not affect my probability of getting a 10 from a deck of cards. So these two events are independent. The probability of the second one was not affected by what happened in that first one. All right? Let's look at the second example. I think this is a very good example of dependence, all right? You select a king from a deck of cards, and then you select a king without replacement. Do you guys remember what without replacement meant? You didn't put it back in, okay? So how many cards are there in a deck of cards? 52. And I pull out a king, and I hold on to it. How many cards are now to choose from? 51. So I changed my probability of pulling a queen out, right? Normally a queen's 4 out of 52. But since I pulled that king out and I didn't put it back, I have more likelihood of getting a queen now because I'm only choosing from 51 cards. So these are dependent. How could I easily make that an independent event? I could say with replacement, right? I pull out a king, I get it, okay, great. Shove it back into the deck of cards. I still have 52 cards to pull from. So my chances of getting a queen have not been affected. All right, so why does this matter? Because if they are independent events, then we can just use this easy multiplication rule. The multiplication rule says if E and F are independent events, then the probability of getting E and then F is just the probability of E times the probability of F. So the multiplication rule is when you're doing two or more events. Whereas back in the addition rule, it was when we're just doing one event. All right, so let's compute some probabilities here. Compute the probability of rolling a die and getting a 4, and then flipping a coin and getting heads. Do you agree that they have nothing to do with each other, not going to affect the probability, so it's just this rule we can use, okay? So the probability of getting a 4 and then getting heads. So the probability of 4 and then heads. According to this rule, we just take the probability of the first, probability of getting a 4, times the probability of the second, getting a heads on our coin. Okay, so I do like to keep it more specific than just generic E and F. I like to use what it's standing for. All right, let's go right below this. What's the probability of getting a 4? Well, how many total numbers are on a die? 6. And of those 6 numbers, how many is the number 4? 1. So do you guys agree I have a 1/6 chance of rolling a 4? Is that part okay? Then you go over to the coin. How many total sides are there on a normal coin? 2. And how many of them are heads? 1. So this is nice. You can do it on your calculator, but if you guys remember, to multiply fractions, you just multiply straight across the bottom, straight across the top. So we just have 1/12. Is that okay with everyone? So rolling a die, no matter what we got, did not affect flipping a coin. So they're independent events, so we can just use the rule. The probability of the first times the probability of the second. I want you to flip back to the bottom of the front page. You're like, why are we going backwards? If you look at the bottom of the front page, what was our probability experiment? It was rolling a die and tossing a fair coin. Okay, it's exactly what we just did. How many total outcomes were there in our sample space? 12. Of those 12, how many are rolling a 4 and getting heads? 1. So what's the probability of rolling a 4 and getting heads? 1 out of 12. Isn't that multiplication rule a lot easier than trying to think of the stinking sample space every time? Yes, okay? And so that's how that all works. We could do that sample space every time, but it's impossible to think of all the different things. So just think of them individually. There's 6 numbers on a die. There's 2 sides to a coin. So there's 12 different options that can happen. And of those 12 different options, I care about one of them. So I have a 1 out of 12 chance of occurring. This is more likely where you'll see it in my math lab or even just in real life. The probability of passing elementary statistics is 73%. What's the probability that all 3 randomly selected students pass elementary statistics? So what we have is any given student has a 73% chance of passing class, all right? If I randomly choose 3 people, what's the probability that all 3 pass? So let's write that. The probability that all 3 pass. Well, I need to put this below this. Notice the multiplication rule can be extended. As long as they're independent, we can just multiply, multiply, multiply. Do you guys agree that the probability of Taylor passing does not affect the probability of Jake passing or Seth passing, right? You guys are all independent of each other, right? So these are independent events. So the probability of all 3 passing is just the same thing as the probability of the first person passing times the probability that the second person passes times the probability that the third person passes. Right? The probability that all 3 people pass is just the individual probabilities multiplied in a row. What is the probability that the first person passes the class? 73%. It was given to us, right? So that is a 0.73 chance. Times, what's the probability that the second person passes? 73%, right? Everybody has a 73% chance of passing. You guys are going to quickly see a pattern here. What's the probability that the third person passes? 73%. What's an easier way to write this? You got it. When it comes down to this problem, since everybody had the same likelihood of passing, you can just write that percentage once and then raise the exponent to however many people we were asking, right? So maybe I asked 5 of you, that would be to the 5th power, okay? So just throw that in your calculator real quick. What do you guys get to 3 decimal points? Was it 389? Is that what I heard? Or 38.9%. So this is what you'll see on your homework. They are very, very silly is kind of a weird word to use, but it is. They're kind of silly. It's like if the probability of you drive under the influence of sugar is blank. So they use like these weird experiences, but they'll give you one instance, like 85%, and they'll say, well, ask 6 people. Well, it'll just be 85% to the 6th power, okay? Because all the probabilities are going to be independent of each other, so they're all going to stay 73, 73, 73. Are there any questions there? All right. So if you're doing one thing and then another, you're going to multiply the probabilities in sequence, however many things we're doing, okay? I could figure out there's 22 of you in here. Take 0.73 to the 22nd power. You figure out the probability that all 22 of you pass. It's probably really, really small, okay? But what if I want to know the probability that at least one of you passes? Well, that's a little bit harder to figure out. So that's objective 3, okay? Objective 3 says compute at least probabilities. There are probability problems which are stated. What's the probability that at least blah, blah, blah? For example, At least 1 would be 1 and above, right? At least 5 would mean 5 or above. And it's really hard to calculate them because, let me give you the example of all 22 of you guys passing. 22 is a really large class, and you guys are doing great. You're all still showing up and everything. So what if I want to know the probability at least one of you passes? At least one of you passes leaves a wide variety of ways that can happen, right? If 1 does, 21 don't, or 2 do, and 20 don't, or 3 do, and 19 don't. Do you see that all the way up? There's like so many scenarios, and what we'd have to do was the probability of one person passing times the probability that you don't pass to the 20th power, and so forth. It's just crazy. It's ridiculous. So if you flip the top of page 8, there's a shortcut, okay? The shortcut is using the complement rule, all right? Because instead of thinking 1 does and 21 don't, 2 do and 20 don't, and blah, 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 the opposite of at least 1 is none. And that's a lot easier to figure out. So what we're going to do is we're going to do this problem, and bear with me, I really think this is probably the hardest part of 5.3, so play around with it, come with questions on Monday for sure, like you did this past Monday. Among 21 to 25-year-olds, 29% say they have driven while under the influence of alcohol. Suppose that 3 21 to 25-year-olds are selected at random. What is the probability that at least 1 has driven while under the influence of alcohol? Okay? So this is independent, right? The probability that one person drives under the influence of alcohol is not affected by the other people. So, for example, what if I just asked, what's the probability all 3 have driven under the influence? You would just take 29% and raise it to the 3rd power, like we just did on the last page, right? But the probability of at least 1 means 1 may have and 2 haven't. 2 may have or 1 haven't. Or all 3 may have and none haven't. And again, that gets really complicated to figure out all those. So what your book teaches you is the opposite of at least 1 is that nobody has, okay? So what I always do when I have this is I write my 2 probabilities. You're like, Molly, 2 probabilities, there's only 1 listed there. When they give you 1, they've really given you 2, okay? What do I mean by that? Off to the side over here, let's write the probability that you have driven under the influence. Okay, what's the probability that you have driven under the influence? Yeah, it's not a trick question, right? It's what it gave us, 29%. But what is the hidden percentage that they've given us? They've given us a probability that you have not driven under the influence. What's that?
71.
How'd you get that, Taylor?
Just take 1 minus
29, right? It's the complement rule. So in every situation where they give you 1%, guys, they've really given you 2 percentages, right? Every person we talk to has a 29% chance of saying, yes, I have driven under the influence, but that means they have a 71% chance of saying they haven't. All right, why does that help us? Because if we want to know the probability that at least 1 has, it's really 1 minus the probability that none have. Okay? So this is just something you want to keep in mind. The opposite of at least 1 doing something is no one has done that. And you can flip it. The probability at least 1 has not done something, the opposite is they all have. So kind of keep that in mind. So if this is like a positive thing, at least 1 person has, the opposite is none. If this is a negative, at least 1 has not, the opposite is all. And keep that in mind, okay? So now that we have this, like on your test, guys, are you guys completely confused right now? Is that what you're laughing about?
Definitely. That's like, yeah.
Are you okay with the 29% was given to us?
Yeah.
So 71.
You just said, like,
Okay, so you're okay with this, okay?
Yeah.
So what I was going to say, keep in mind, worst case scenario when it comes to an at least 1 problem on the test, start it with 1 minus something, okay? It's always going to be the complement rule, and it's always the opposite, okay? So at least 1, the opposite is none, okay? At least 1, the opposite is none. And why does that help us? Because over here, none have driven under the influence of alcohol. Well, how many people did we ask?
1, 3.
We asked 3, so what's my probability or my exponent going to be 3? So there's none, 3 of them. And what's the probability that you haven't driven under the influence?
0.71.
0.71. Okay? So even though they gave us 29%, guys, we didn't even use 29% in our calculation, right? Because the opposite of at least one has is that none have. And so the probability of not driving is 71%. And how many people did I ask? 3. On my math lab, they'll start with this, and then part B will be like, okay, you asked 7 people. What's the only thing that's going to change? Your exponent, the little guy, right? So you'll just do the same setup, but then you ask 7 people now. So what's the probability that all 7 haven't driven, okay? So when you do this, when you round to, let's round to 4 decimals, do you get 0.6421? Is that what you get?
Yeah.
Okay. So let me show you another way we can do it. And I'm going to do this not to confuse you, but it probably will, is to show you how this is a shortcut to doing it the long way, okay? Since we're just asking 3 people, doing it the long way is not bad, okay? So what I'm going to do, I'm just going to do it like right below here, so you don't need to write it. Just follow with me, okay? If we were going to do this the long way, the probability of at least one having driven under the influence means 1 did and 2 didn't, okay? So what's the probability that the first person did? 29%. But then if the first person did, that means the second 2 didn't. Do you agree with that? Okay? So that's the scenario of that one person drank under the influence. But it's not just one, it's at least one. So what's another option? Maybe 2 people drank under the influence. Okay, well, if 2 people drank under the influence, what does that mean about the third one? They didn't. Do you agree with that? So here's one scenario where 1 person did. Here's a scenario where 2 people did. And what's the third scenario? All 3 of them did. Guess what you get when you multiply all that and add it all up? 6421. Why? What's the one scenario? Look, we have 129 and 2 71s, 2 29s and 171, and 3 29s. What's the one scenario we don't have? 3 71s, right? Isn't that what we just had? The complement, the opposite of what we wanted, was down here, right? We don't want that, so that's why it's 1 minus, but that one scenario is a lot easier to figure out. Did that make sense to at least one person? Maybe? Okay. I'm just trying to prove it. It's one of those things, as an instructor, I hate to say it, even if the proof doesn't make sense, just remember with the at least one problems, it's easier to figure out the one thing you don't want and subtract it from 1 because you want all the other crap. Okay? So at least 1, always remember 1 minus. So on a test, even though you just remember 1 minus and you know nothing else, you're going to get 1 of 4 points because you remember it was a complement rule.